Good morning, everyone. It's great to be here. Always love coming to India, and just the excitement of the place really excites me. Yes, I'll be talking about IEA Annex 81, Data-Driven Smart Buildings. This is the annex that was about deploying software services in buildings for energy productivity. I'll go go wide, not deep. My aim, I guess, is just to introduce you to some of the topics, and then you can go to all the loads of resources that are available to get more detail on that. So this annex was a collaboration of around 50 organisations across 18 countries. So a lot of effort, and it's just completed. So this is fresh. So what makes up a smart building? We did create a definition, but I like this diagram here. It just shows, if you like, the journey from data to an outcome. Starting off with data capture on the top left quadrant. Once you capture your data, you need to bring that data together, make it accessible, and then you can apply modern mathematics and data analytics on that, and that presumably produces something that's really quite useful that then you need to send out to the people who need to have that information to deploy the answer. So that's, if you like, your cycle from data to decision making. Perhaps in my energy efficiency world, I despair when policymakers say we just need smart meters and kind of leave it at that as though that is the solution. But there's far more data out there, and the more data you have, or the greater diversity of data, the more things you can potentially do. So we have various other data sources, such as Internet of Things sensors and devices. We can connect up the BMS to learn about the building controls, and indeed the mobile phones that we have and walk around with are mobile sensors. On the data management side, we want to federate all that data in one place. We call that a data platform, and then put access controls so that the right people can access that data. We'll talk much more about that. Then in the data analytics part, that's where your artificial intelligence or machine learning algorithms to create the knowledge, and then dispatching those instructions, automating financial processes, and providing interfaces that make all of that happen. So when you bundle all that together, I call that an Energy Management Information System. EMIS. This is a term that Lawrence Berkeley National Lab coined, and it gives you transparency of what's happening in the building. It's giving you the smarts, and it's giving you the connectivity to mean that the right people have the information. So that's the general philosophy, if you like, and there are lots and lots of different applications to which this can be applied. Those can be in the predictive maintenance area, they could be in the security and access controls area in a building, the space management. Obviously in the IEA, the thing we're most interested in is the energy management bit. That's the green part. This particular review that an entity called Memory did looked at startup companies, and you can just see the diversity of startups that were going on. But the key is, why don't we see this more in buildings today, and how do we actually scale this industry or grow this industry, and why is it likely to grow? One part is that we have these things called data-driven algorithms, and that's why I use the title of this annex is Data-Driven Smart Buildings. Essentially, the philosophy of that is you are taking the data as is, and you are relatively agnostically utilising that data to achieve learnings. And that avoids the need for bespoke solutions where you have to code up something very specific for your building and stuff. No, you're just relying on the data telling you the answer, and then using machine learning and AI to do that. So the actual algorithms, that's one part of why it's scalable, and the fact that it uses the data. And the other part of it is the idea that we're actually going to use IT industry-based systems here that give us the machine-to-machine connectivity and the ability to shift data around, not just with humans, but also machine-to-machine. But all of this is reliant, I guess, on good quality data and data that is managed so that it's discoverable and accessible, and we'll talk more about that. But ideally, if you have these principles in place, you have the idea that is a lot like a mobile phone, where you can actually deploy software applications in a self-configuring form. Part of this annex assumes that because we're using IT-based practices rather than OT, operations technology, or SCADA, is that we will make use of the cloud. And that gives access to the information that's produced, gives access to people in remote locations over their mobile device, and you just can't beat that for connectivity and streamlining processes. Also, from an infrastructure point of view, it's scalable. You have people professionally managing data centers and the like to make sure that that data is warehoused correctly. And when you go into the cloud, you can consolidate with third-party data, which allows you to make more inferences and do more creative things than you otherwise would with just the limited data that you might have on site. So cloud-based management is good. If I talk to 50 different people in the industry, probably I'll get about a half-half mix that come back and say, well, we're already in the cloud, or never on my dead body will I ever go into the cloud. So clearly making this all happen is the data platform, and this is kind of the way we kind of viewed it in Annex 81. That is that you had a whole range of data sources from all those places that I mentioned. That data is then warehoused in a data platform, and it is corralled into bins or containers that you can then manage who gets access to it. And then you set up the pipes so that applications can self-configure, look into the database, query for data, and then deploy their smart analytics services. So the platform is the intermediary, if you like, that's providing the standard interfaces to collect the data and standardized interfaces to enable people to use the data. Here's just another way of representing this one. Again, you've got the data sources on the left, the data warehousing, that's, if you like, the EMIS data infrastructure, and then that is what enables your software applications, and we'll talk about some of those software applications later. So in our annex, subtask A looked at that data infrastructure, subtask C looked at all the applications, and because we had lots and lots of people that were really interested in model predictive control, we also created a separate subtask B, which focused in on building controls. So, let me run you through just some of the results. Again, I say I'm going not very deep, plenty wide here. So data sharing and data platforms. You won't be able to read all of those quotes, but we went out interviewing all the industry experts, and it came back time and time again. When you talk about analytics, it's all about the data management, right? It's no secret that in anything data-driven, 80% of the effort is in the data part of it. This really stresses the importance of this. Here's my favourite one. This one comes from a facilities management manager who says, like it's going into a library and someone's got in there before you and messed it all up, and they swapped all the books around, and you spend an entire day trying to find something which should be categorised properly. So get that data management piece, a lot to do with cataloguing your data. And if you're going to catalogue the data, you'll be wanting to use the FAIR data principles. FAIR, that acronym, F-A-I-R, is findable, accessible, interoperable, and reusable. So there's a whole bunch of sort of things that go underneath that, but I guess what I would, again, difficult to read from the back, I'm sure, but I would highlight that metadata comes up very, very frequently. So what is this metadata? Essentially, this is the way of naming and structuring data that is in your building. So all your equipment inside the building should have a particular way of naming it that is according to a structured format, and the actual relationships involved would also be mapped in that structure. So this is a thermostat in this room, it's connected to this air handling unit, etc., etc. Why do you do that? It means that if you're using that structured language, then you can find this stuff from all the data that's circulating around. So ultimately we've got two concepts here, the metadata schema, that's, if you like, the formatting methodology, and then the metadata model, that is using that for your particular building when you code up all those data streams that are sitting inside the building. So we then went and reviewed various data platforms, and we had a whole bunch of criteria that we looked at. And to be honest, there's lots and lots of really good providers of data platforms out there. Probably the area where the most differentiation in terms of perhaps what we would call quality is around how much they've used a metadata structure which is open and publicised, or publicly available, rather than a proprietary system there. Whether or not there was a data accessing permissioning system that allowed the building owner to share their own data as they want to, rather than having to go to the provider and pay money to get the data to go to someone else, etc. So the utility of that data structuring and data permissioning system was important. And then many of them were closed ecosystems, and we were advocating for open ecosystems with third-party applications. So that was our work of subtask A in quick summary. Subtask B on model predictive control. So just for those who are not familiar with the term model predictive control, in your normal building you have HVAC equipment, it's doing a job, it's all coded up, the logic for controlling the air conditioning, and it provides air conditioning through the equipment, and then the occupied space is hopefully comfortable. All a very sort of closed system. And what we're introducing in model predictive control is a supervisory controller over the top of that. So what happens is the feedback from the conditions in the building go into the control-oriented model, which is like the digital twin, and that gives you ability to forecast into the future how the building will actually control. And so the MPC controller then has a look at the digital twin, sort of does its optimization, and then on the basis of that sends set points to the actual controller in order to optimize both for comfort, cost, and emissions. So this can give you quite substantial energy savings. Hasn't been widely deployed yet for a bunch of reasons. So we pulled together a bunch of case studies, picked out the data sets, and if this is an area of research interest for you, then I can point you to these 6 high quality data sets to get you started. We then did a bunch of what we call common exercises there. Rather than using a real building, we used an emulator or virtual building, and we looked at 2 scenarios, one being a peak heating day, one being a typical heating day, and we had the rules-based controller was the default. That's your normal controller, and then we used various we threw it open to the community and said, please find your best artificial intelligence controller. So model predictive control and reinforcement learning techniques. And in all cases, you could reduce energy consumption by about 20% using the AI controllers, and this was not sacrificing comfort, this was actually improving comfort at the same time. So a win-win for the controllers. All right, moving to subtask C, the applications and services. We looked at a range of things, which I'll go through. One was just data for calculating KPIs, so the reporting application, if you like. We went out there, literature survey, 430 different KPIs we found, and then we went to 5 case study buildings, and we found that of those 430 KPIs, only 25% of them were actually calculatable with the data that was in the building. So, yeah, big gap there between all the KPIs you see and what you can actually do. Fault detection and diagnosis, this is like going to your medical doctor and with your symptoms and asking for a diagnosis. Here it's your building doctor. Go there with the symptoms and get a diagnosis. This is relatively mature, at least in Australia, but typically using rules-based methodology. So if this, then that. That's a kind of a rules-based methodology rather than the data-driven approaches, which are relatively agnostic to any logical kind of thing. They just use the data as the source of truth. So we still found that there was plenty of room for continuing to improve on the deployment of fault detection and diagnosis. And again, we've got 7 high-quality data sets. If that's a research interest of yours, this is the place to go. Last one was around grid-integrated control of buildings. Again, similar story, collecting up the data sets, and I think we've ended up with... We started off with, I don't know, something like 200 data sets, and when you actually whittled them down to were they a quality data set, we didn't end up with so many. We also found that the KPIs for flexibility versus the available data, there was a bit of a mismatch there as well. So plenty of work to do in getting the right data for this particular application. Last subtask D, case studies and roadmap. So Virginia, who's in the audience, ran the case studies website there, datasmartbuildings.org. I think there's over 20 case studies there, which was looking, I guess, at not just at the sort of the technical side, but the practical implementation challenges that were observed. And we grouped them under 4 different sort of categories. Of course, when you do these lessons learnt things, you're always going to be asking for what went wrong, and so I always worry about the skew of bias, if you like, there, that this is lessons learnt, the things you don't want to do, and you know, things around stakeholder engagement, taking people on the digital journey is key, etc. And I highlight in blue again data quality and management as being one of the core things that people found tricky. We went out and working with industry across 3 continents around the globe, came out with a bunch of recommendations for policymakers as to what they should do, grouped into 8 themes, and just in the interest of time, I highlight in blue, what would it be? Data quality and data management, and that was the thing that really got people arced up to talk about. So theme 2 and theme 6, establish digital ready certification and reduce data sharing risk. So let me explain that. So I already went through this series of quotes of what one of the core problems was, and then they started to give us these solutions. Well, we could ask for smart meters. Well, I see that as ground zero, as I mentioned before, and then a SaaS platform, software as a service platform provider says digital ready audits should be done before we come in. And then and we really picked up on this, was this idea that somehow or other we should have some sort of certification arrangement to actually tell people what to do and when they've achieved what we call digital ready. So what do we mean by digital ready? Well, the current way the industry typically works is you say, I want fault detection. So you go to a fault detection company, and they, in their own little silo, they bundle up their solution along with whatever hardware they need and provide it to you as a single bundle. And every time you want to do something, you've got to go to a new provider. And we're saying that what we're really looking for is breaking apart that data capture, data quality, data management piece, separating it out from the software applications, and in between, creating this certification called digital ready. Luckily enough, as Melly was alluding, we've actually done a bit of that in Australia. I don't think we've nailed it yet, but in our National Construction Code, so when you build a new building under the J9D3 provisions for facilities for energy monitoring, we've included some of some criteria or specifications around that. And the Victorian Energy Upgrade Scheme is investigating putting incentives for what's called a foundational EMIS activity using specifications that we've created in this annex. Won't go into this, but we then sort of captured all the themes and all the recommendations under each theme under the old classic, what is it, sticks, carrots, tambourines kind of thing. That is regulation as your sticks, information and is your, kind of your tambourines, celebrate and provide information, and the incentives, you know, actually how do we actually create money for the business. And we followed the IEA's net zero map. We said right now, this is low-hanging fruit to deploy this sort of stuff. You can have up to 40% savings at quite good payback times. But if you look at the IEA's net zero by 2050, you will see strong recommendations around digitalisation as an enabler for connecting buildings to grids. Finishing up, I guess, a whole bunch of resources. There's your website, annex81.iea-ebc.org, a bunch of reports, a bunch of data sets, that's the ones in green, and various software tools, I guess, for benchmarking as well came out of this annex. So I'll leave it there.
We do have about 5 minutes for Q&A, just in case. I can take one question from the audience. Can we get the mic there?
Hi, my name is Ronak. On the data quality, you know, in the outdoor world, there are categories of data accuracy like L0, L1, L2. When NASA releases a data set, the real-time data, which may not be very accurate, may be called L0, and then when you do some cleaning on it, it becomes L1. Then you put some calibration, it becomes L2. And L2 takes much longer to release. It may take about 15 days to release the L2. So I'm just trying to ask on the indoor or the built environment side, is there room to create different categories of accuracy of data, and the absolute real time maybe, let's say, 70% accurate, and then you apply some more corrections and calibrations, it may become 80, 90% accurate, but room to have multiple levels of accuracy so that people who want to take quick decisions with 70% accuracy can do it, and those who are willing to pay more for 90, 95% accuracy can wait a little longer.
Yeah, that's a really interesting and a good question. We didn't really go into accuracy of sensors and the actual sort of sensor device itself so much as accuracy of recording. What is this sensor actually, what is it? What's its meaning, if you like? Is it a temperature sensor? And if it's a temperature sensor, what's it connected to? And so significantly around that, ability to get the data into a common place so that a software application can request the right data and believe that it actually is getting the right data and stuff. Obviously, accuracy of sensors is, you know, you can have certain accuracies when you first install the sensor, and then over years it goes out of calibration, and temperature sensors, are they installed in the right location and stuff. So yeah, there's a whole big topic around that as well. Yeah.